If each trial of a random experiment is independent with success probability p, the number of times x needed before obtaining a success can be computed using the geometric probability distribution. Let's find the cumulative distribution function. So we need to find the probability that x is less than or equal to k, and that's going to be the finite sum from 1 to k. We can simplify the problem by removing the constant factor of p, and note that we're summing a geometric series where the first term is 1, the last term is 1 minus p to the k minus 1, and the ratio is 1 minus p. So the next term we didn't add would be 1 minus p to the k, and so our summation would be, which we can simplify, and that gives us our cumulative distribution function. So again, a useful strategy for learning math is to solve it again. So let's try and find our cumulative distribution function another way. The event a success on or before the xth trial is complementary to the event no successes on the first x trials. And this is the same as the first x trials were failures with probability 1 minus p. So the probability there's no successes on the first x trials, 1 minus p to the x, and so that means the probability that there was a success on or before that x trial, 1 minus p to the x, which is the same as what we got the first time. The reason we didn't start with this approach is that it gave us a chance to review summing infinite series. Also, I didn't think of it until I'd already written up the first part. So suppose we roll a 20-sided die until you get a 20. What's the probability you'll get a 20 before the 10th roll? So on a 20-sided die, the probability of a success is 1/20th. So the probability we'll get a 20 before the 10th roll means we got a 20 on the 9th roll or before. So we want to find f of 9, which will be so there's about a 37% chance we'll get a 20 before the 10th roll. Or suppose we roll a 20-sided die until we get a 20. What's the 90th percentile of the number of die rolls required? So we have our probability 1/20th, and we want our 90th percentile, that's 0.9 probability, to be our cumulative distribution. And we can solve this for x. We'll rearrange things a little bit. Hit both sides with a log, and solve. Since x is a discrete random variable, it's either 44 or 45, and the important thing here is that the rounding rules won't actually help us. So even though this would round up to 45, it's possible that 44 is the answer. So we have to verify. Note that if we round down and use 44, our cumulative distribution is going to give us so slightly under 90% of the time will require 44 or fewer rolls. Meanwhile, if we rounded up and took 45, we'd find, and so just over 90% of the time will require 45 or fewer rolls, and so the solution is going to be 45. At least 90% of the time will require 45 rolls or less. It's important to remember that when we have a discrete random variable, we can't simply round our answer. We do have to check both possible rounded values to see which one actually answers the question. So for the 95th percentile, we'd have the equation. Solving for x gives us and we could say that at least 95% of the time it will require 58 rolls or less, but we'd be wrong. If x equals 58, we find, so x equals 58 is not quite at the 95th percentile. So if x equals 59, we are just over the 95th percentile, and so the correct answer for the 95th percentile is 59. So at least 95% of the time, it will require 59 rolls or less.